Thank you. All right. Next up, we're going to have Brian talking about instrumentation as living documentation.
Can everyone hear me well? Okay, cool. So my name is Brian, as was mentioned. This is a talk that I've given to engineers largely, never to technical writers, so if this doesn't work out, I apologize. I'm a software engineer. I write documentation necessarily, but I teach computers to do things. In particular, I am not a person that builds software for end users. A lot of the talks have been focused around end users. I build software that communicates with other software, so computer to engineer, generally. And the good work that I've done, what little I suppose there is of it, has some shared characteristics. So I build real-time systems. These are systems that have an implicit clock for every computation. These clocks represent deadlines. If you go past the deadline, your computation has no value. Depending on the type of real-time system, either you don't necessarily care, that's called a soft real-time system, or everything is on fire and people are dying, and that's called a hard real-time system. The middle ground there is firm, so the computation has no value, but people don't die. I build distributed systems. So these are systems that have to operate over multiple computers, over an unreliable network. And they have to maintain some shared understanding of reality, which is actually very tricky. We humans are relatively poor at this at the moment. We're learning more about it. And I build critical systems. So that somewhat goes hand in hand with real time, but these are systems that must continue to function, or when they don't function, they fail in a certain well-known way. Right now, I work for a company called Adderall. Adderall is an advertising company, which is sort of an odd company, perhaps, for the work that I do. But advertising over time has changed. So it's less this now, this being very large accounts, Neiman Marcus, things like that, where you have $50,000 to spend in a month. And you basically go around and you go to the New York Times and you say, I'm going to buy $10,000 worth of ads. What'll that get me? The problem with that is you can advertise so long as you have $10,000. Increasingly, advertising is about this. It's engineering applied to advertising, and it's made advertising much cheaper. We have clients that advertise at $10 a month. One of my favorite examples are people that make forks into bracelets on Etsy. They don't have a lot of money to advertise, but they are able to do so, and they don't have to basically beg the New York Times for space. Adderall is an ad tech company, so ad tech is really about data. You mash together real-time systems engineers, you mash together mathematicians, and out pops this wonderful machine. I, in particular, work on real-time bidding. So when you load a web page, right, you've got all those ad slots. Those aren't pre-rendered. Those are bid on in real time while your page is loading by computer systems all over the globe. You have about 100 milliseconds to do it. And this is what sophisticated ad tech shops do now. There's another older type of doing this sort of work called console bidding. Basically, you hand Google or Facebook a big chunk of money and you say, spend this well for me, and they don't spend it well for you, but you've got no recourse for that. So the nature of the problem in the domain that I work in, it's very low latency, so less than 100 milliseconds per transaction. It's a firm real-time system, so if we go past the deadline, if we fail to make a bid, nothing bad happens, but we also can't make any money. It's highly concurrent. We do greater than 55 billion transactions per day, and that is not smooth load, so that's stampeding herd because people come online at different times. And we're global, so unlike high-frequency trading where they shut it off after about 10 hours, we run constantly. That's hard. I build complex systems. That's sort of my hobby horse. And complex systems, so I'm trained as a computer scientist, but complex systems have this complex organization that exists around them. And complex organizations do very elaborate things. Some of them good, some of them bad. Complex systems in particular have nonlinear feedback, so the system itself starts to interfere with its own operation, and you have to understand that that's going to be the case. They're tightly coupled to external systems. So when I say tightly coupled, they are connected in a way that does not have any give to it. They do not move independently. So my foot is tightly coupled to my leg, so on and so forth. You can't pull on my foot and not affect me. They're difficult to model and they're difficult to understand, these complex systems, just because we're sort of bad at it. And we've always been sort of bad at it. You know, we build an industrial civilization and we accidentally poison the atmosphere. We didn't set out to poison the atmosphere, it was just an unintended effect. And complex systems are usually the solution to some sort of wicked problem. So C. West Churchman has this fantastic article that just was an editorial in a management magazine where he discusses these sort of wicked problems. They're social problems where you propose some solution to this very vaguely defined issue that you've got, and you do your best, and your solution generally causes worse problems than the thing you set out to solve. So they're wicked because they're almost evil in that sense, where you really can't get ahead. Bad things happen when complex systems fail, right? Because you built them to resolve some really bad problem. And now you've sort of pushed all of the easy, sensible things off, and now when your complex solution has failed, everything that was really terrible is going to happen. Complex systems often create worse problems than they solve. So the background to this is interesting. When the Chernobyl disaster occurred, the Soviet army just threw, men and machine at it. Everything was irradiated. The men they let leave, the machines they just parked. So these machines are parked here, then the Soviet Union collapses. Everyone's trying to make money, so some people know that these machines are here. They've got valuable engines, they have rubber, they have all sorts of things you wouldn't want. So people came and they recycled them. So you have these highly radioactive engine parts being distributed throughout Eastern Europe. Whoops. So this is a quote from Carlos Bueno, who is an engineer at Facebook. He wrote this fantastic book called The Mature Optimization Handbook. It's for engineers, how to decide whether or not to spend time making something faster, but it really sort of gets down into why an organization would choose to invest more time in a system. And he talks about performance, but it's really about maintainability and things like that as well. We sort of get into this mindset where because we've been able to make something, we also understand it. It's sort of the hubris of the engineer. We don't actually understand these things that we make. We understand a very small set of its potential states. And the devil is in the details. So the key challenge to sustaining a complex system, keeping it running and not injuring people and killing businesses and things like that, is maintaining our understanding of it and increasing more our understanding of it. So what do? Well, we write documentation, right? We sit down and we think really hard about the system. We build procedure manuals, we explain concepts, we build glossaries, we write this very elaborate documentation, and it's extremely valuable. So the bus factor, the idea that the critical engineer on your team that built the thing, if he gets hit by a bus, can your organization continue to persist the system? Well, documentation helps solve that, right? Unfortunately, complex systems are fiendishly difficult to communicate about. This is actually a slide that's somewhat contentious at engineering conferences, but I actually imagine most of you will agree with this statement. It's so hard to do, and it's so hard to bridge the gap of understanding, to realize that I have this implicit model of the system in my mind when I sit down to write about it or communicate with someone that's going to write about it. I have this implicit model that gives me much more information, and I am unable to see the system with the beginner's eye, I think Buddhists tend to call it. So miscommunications for complex systems are accidents in the making. You drive a system where it should not have gone. The examples of this are endless. The Challenger accident occurred because of a faulty O-ring. And it wasn't faulty because it was manufactured wrong. It was faulty because it was too cold. It couldn't keep the seal anymore. The system, being the space shuttle, had been left out in the cold too long, and no one really thought anymore about that seal sitting there, except for the engineer that had designed the seal and said, hey, we can't let that sit out, but because of organizational problems, no one heard that who had decision-making power. So documentation reduces accidents. It doesn't solve them, but it gives everyone more of a shared understanding of the system so that you can hopefully not drive it into a bad state so often. Because the problem with these systems are, if you don't know how the system should behave, you can't say how it isn't or shouldn't behave. The issue here being, everyone has an implicit understanding of how some mechanism is going to work. These are not always correct. My favorite example of this are cargo cults. So after World War II, we just sort of showed up on islands with relatively primitive peoples, and we gave them food and whatnot so they wouldn't throw spears at us while we were dropping bombs on the Japanese. Then we left, and to them it was as if the gods left, because these people would fly in, they didn't look like anyone else, and they would just give food. You know, they had an endless supply of food. So what they did was they built airstrips. They built radar towers out of bamboo to try and get the gods to come back, because they felt that maybe that was what had drawn the gods in the first place, because that showed up first. They didn't know how the system of a war worked, so they couldn't say that it wasn't working anymore. The trouble with documentation is it goes out of date. Try as everyone might, eventually you just run out of steam. So complex systems continue to evolve. They continue to evolve either because people are changing the system itself or people's understanding of the system is changing, which nonlinear feedback, right, that actually feeds back into the operation of the system. So it rots as the system moves on, and we can keep running and keep updating it, and we have to, but it's a very hard problem. So sometimes this occurs because engineers change the system and simply fail to update the documentation or discuss with someone who updates the documentation these changes that have been made. You just sneak this sort of stuff in. I say favorite, but one of my favorite examples is the Chernobyl disaster of this occurring. So the Chernobyl nuclear power plant was in Ukraine, Soviet Union at the time. It had a complex procedure manual. It had been built in a deficient way, and they were testing a redundant fail-safe system. So they shut off the original fail-safe system to test it. When they get, yeah, right. When they get to this, when they get to this point in the operation, the procedure book, where they're going to go through and decide what to do, has the original instructions all typeset. They've been crossed out, and there are instructions next to them that give a new procedure, but they're crossed out as well. And so the operator says, what should I do? What should I follow? And the person he asks thinks about it for a minute and says, well, follow the original ones. It turns out neither was correct, but there's no documentation anymore about the state of the system. I think the operator got executed by the Soviet Union for that. So this is actually deadly serious. Engineers can be unaware of the system as it's actually used. So engineers might not be the people that actually run the system. You might have an operation team. So you might write a bunch of documentation and decide that, okay, well, this explains how the system is used. This fails in some cases. So the Titan II missile complexes, which during the Cold War, we built a lot of nuclear missiles because holocausts are fun, I guess. So these Titan II missiles are really dangerous things. They've got an extremely volatile oxygen-based fuel that is bleeding through the outside of the missile. So when you go to these missiles, you have to put on these big rubber suits called refcos because the missile is toxic. Surprised that a nuclear missile is toxic. So they have to top off the tank every so often. And there was this accident at a Titan II missile complex where someone dropped a spanner and punctured the side of the Titan II. The procedure manuals for maintaining these missiles assumed that you would be wearing a refco suit, doors would not be propped open, but it was such blast doors would not be left propped open, which they were. It was such a pain to get into the suit, close the doors, depressurize, open the doors, that people just left them all propped open and they didn't wear the suits. This fed back into the system, because if you don't put on a suit that takes 15 minutes, suddenly you're much faster at maintenance. So someone observing how long this team versus that team is able to maintain the missile, you say, well, that team's much faster, so we're going to chop the time you've got to service the missile in half. So everyone is forced unwittingly into not wearing their refco suits. That ended up killing 3 people at the Damascus Titan II missile complex. Eric Schlosser's command and control, highly recommended. So normal accidents happen. A normal accident is Charles Perrow's idea that every system has intrinsic to itself some failure. And try as we might, we can never get rid of them. So when you design a system, it's your choice. You can decide, say, a nuclear reactor will just shut down and not generate any power, or if you must always have power, you decide that the nuclear reactor will blow up in a divergent case, fail safe and whatnot. We can't get rid of these. A great example of this is the Apollo 13 disaster. You had an oxygen tank pop, and when that popped, a redundant enough oxygen transfer system failed. And it failed because the oxygen tank popping broke some pipes. So the Apollo 13 had 3 tanks, 2 emptied in the time that it took for mission control to figure out that something had actually happened. They spent 8 3/4 minutes discussing whether or not a meteor had struck the ship because they were so confident in their construction that they couldn't believe that an accident had occurred. Well, it had. So the problem with documentation is that it doesn't necessarily reflect the reality of the system. So the system is growing and changing, and people are getting different ideas, crazy ideas in a lot of cases, and documentation is a relatively static thing. We have to keep changing it. So what can we do to resolve this? How do we build better systems that help distribute knowledge and forestall accidents without a lag time? I propose instrumentation. So you have this sort of live thing that is part of the system. So instrumentation itself reflects the reality of the system because it is the system. It is something that's built in. The system is just through an administrative interface or over a network just spewing so much data about itself. And instrumentation allows the users and the engineer to explore the system as it exists. So you can start looking at this live stream of data coming out of this system and figure out what it's actually doing. So in the Apollo 13 disaster example, they didn't have enough instrumentation. They had indirect instrumentation. They didn't have a meter that said, well, this tank is so full. They had an indirect measure of flow through a pipe, which is not enough. They needed more, but in software at least, we don't have space constraints. We have CPU consumption, we have memory consumption, we have things like that, but we're not actually putting things up on a rocket, right? So we could just keep layering this stuff in. So this exploration that instrumentation allows, done honestly, guides us to a new and better understanding of the system. So everyone is able to get more of a shared understanding of how this thing works, and works in practice. If you kick the box, what does the instrumentation say? And you can figure out what it's going to do in cases that it wasn't necessarily designed for. You actually see this again in the Apollo project. I come back to sort of the Apollo project and NASA a lot. The astronauts originally hated the craft, so the craft was largely computerized. And the astronauts ended up being these sort of managers of complex systems. They give input to the system, but they're not actually flying the ship. A computer flies it. They hated it at first, but it turns out that it's actually really hard to fly a spacecraft. So they started to refer to themselves as the collective entity. So the ship becomes just another crew member, more or less. It's a really fascinating change in an understanding of what it means to be a pilot. So instrumentation also democratizes the process around these complex systems. So you don't get into a case where you have the fiefdom of the database administrator, because now everyone can look at the database and see, well, what's happening in it, and make decisions, ask questions. You don't have to go through cultural choke points, which is a problem in complex organizations because that's where sociopaths tend to find themselves. So case studies from my own work. Incidentally, behind this slide is the inspection photograph for the Challenger on the day of the accident. You can see the ice crystals hanging off. It was just left out in the cold for too long. So, in particular in my work, at Admiral, what concerns me is the amount of bids coming in from the exchanges, the amount of notifications that there's something that I can bid on. For each bid, I can do something. When I can't do something, I can't spend money, and when I can't spend our customers' money, I can't make money for the company. So not having bids come in is a disastrous thing. We call that state throttling. So here's a healthy pattern of bids. This is spread over multiple days. You can see the diurnal pattern of humans waking up, doing things on the internet, and then going to sleep. Oddly enough, it generally peaks around 11 a.m. in the United States, so people really surf the web at work a lot. But this is good. This is a good day for us. Well, a good couple of days for us. This is bad. So you see off to the left there that we've got a normal flow of traffic and then crash, way, way down. this is a real problem for us. It's helpful when you start using instrumentation like this to confirm that what you see is what you see. Our visual cortex is very good at sensing patterns, but we are not very good at sensing rational patterns out of things. So you sort of correlate between multiple graphics. This is a first differential of the two previous curves you saw. On the right-hand side is the good one. You see that the rate of change is relatively diurnal. On the left-hand side, you see the bad one, where the rate of change is flat. There is no change in the system. When you have a complex system and your complex system develops a fault that you believe is occurring at one of your coupling points, one of the points of communication with an external system, you have to confirm with that external system that the problem is present, because you don't always know at a tight couple point whether it's your fault or their fault. And sometimes you can't ever figure that out. It's a complex feedback within that coupling, which is really hard. So we confirmed with our external system that, in fact, we were being throttled. This wasn't a problem. This wasn't a problem at the edge of our network. This wasn't a problem with our boxes, because we could confirm that all of the boxes were basically idle once their traffic had died. And we confirmed that we hadn't changed the system. So it was running the same code base, the same inputs before the throttling event and afterward. So what in particular happened here? Well, we hit an implicit exchange limit. Arguably, it's a bug. There is such a thing as a cookie match. So we don't share, in the advertising industry, we don't share your information. There is no point at which BrianL.Troutwine's information goes between multiple companies. It's completely anonymized. And we do that through maintaining a large index of anonymous cookies. And that's called a cookie match system. So we keep cookies, our exchanges keep cookies, and we just sync them. So with this particular exchange, we had synced greater than 1.5 billion cookie matches, which triggered an edge case in their code, and they believed us to be divergent. Their code just assumed that we'd obviously sent them a whole bunch of crap, and we couldn't possibly have had 1.5 billion, so they throttled us because they shouldn't be bothering spending the money to send us the traffic. It turns out we did legitimately have greater than 1.5 billion cookie matches, so it was fixed. So another example, timeout jumps. So we're very sensitive in our system to the amount of background noise timeouts. Because we're using a programming language called Erlang, which is a soft real-time system, systems programming language, we can't actually say, I've got my deadline and all of my computations will finish before the deadline. What we can say is most of them will. So we've got this background noise of things that just time out naturally. Bid requests that don't meet the 100 millisecond time limit. So this is a pretty healthy pattern of background noise timeouts. The peak is around 1,000. We're doing several million a second, so 1,000 is not a bad background noise. This is bad. This is a jump. It's not huge in terms of magnitude, but suddenly if you do the integral of this curve, it's actually quite a lot of timeouts. Our peak rate is relatively untouched, but the minimum rate has come way up. The problem with timeouts with exchanges is they're relatively unforgiving about these things. If you time out too much, they will throttle you, and that is a disaster for us. So the bid request, this is a graph of between noon and 9 p.m. of a good day when we get bid requests coming into the system. It's sloping off because people are going to sleep, they're not browsing the web as much. This is a bad day. This is a real bad day. So we had an unrelated event to this case study on the left-hand side. It recovers a little bit, and then we have another event related to the timeout jump that just completely cliffs us. So the problem here is these timeouts only occurred on the US East Coast. So we deployed to two regions, US West, US East. US West was fine. It was untouched by this problem. It only exhibited in US East. All of our other metrics, just as I discussed above, were fine. Boxes were idle, network was fine. The strong correlation here was system deployment. We had actually deployed a new system, so that was the problem. And so we rolled back, and then that reduced the timeouts to their previous levels. So what happened here? Who can That's the problem with being tightly coupled to external systems. I don't know if you noticed, but in the graph where I showed you the bid requests, we had a timeout jump in US East, and we got throttled on US West. We have no insight into the algorithms of our external partners. So the external system has some behavior that is unknown to us and unexaminable. And at these failure times, we have unexplained behaviors, and we never figured it out. We can't figure it out. The exchange is unwilling to give us enough information to do that. So we just try and keep timeouts low. So all of this instrumentation is great, but it has defects for the complex organization around these systems. In particular, it is possible to have too little information. So you see that for us most recently in that last case study. We don't have enough information about what the exchange is doing, so we can't say if we really goofed or not. And we don't have any insight into Amazon's boxes, so we can't say why the problem only occurred on US East. You see this again at Chernobyl, right? Chernobyl accident occurs, they start kicking these radioactive burning graphite back into the reactor because they have not been told about radiation poisoning. They died just because they've not been told not to do this. It is possible to collect too much information or to present it badly on the flip side of that. So when we start diving into these things, when we start going through our instrumentation and we cross-reference with documentation, sometimes it's overwhelming. There's just too much information to decide what the system is doing. You see this at 3 Mile Island. So I study the nuclear control systems a lot. So 3 Mile Island at the time had this room. It was the era before glass displays, before computerized displays, and you had the operations team was responsible for a section of the wall that had instrumentation, and they would just cross-check by yelling out, you know, heat reading this, heat reading that. During a disaster, during the start of the 3 Mile Island disaster, everyone got real excited, and so they started yelling, just yelling these readings back and forth, and they missed readings. So they didn't have correct actions because they didn't have a correct understanding of the nature of the system, and they couldn't because the system was giving them too much information about itself. So instrumentation is not perfect. You can add a whole bunch of instrumentation and feel real good about yourself and all the work you've done because it takes a long time to do it, and never get anywhere, or never get to the point that you would hope you were going to get to. Instrumentation itself may be misleading. So instrumentation might tell you one thing, but another thing is happening. Instrumentation is itself software, so it has bugs. You have to know some basic mathematics. Mathematics that is generally not taught at an undergraduate level unless you are like me and did pure mathematics for a little while. Too much information hampers interpretation. So we're very good at holding about 5 things in our mind at one time. Computers don't care about that at all, and they will give you 10,000 things at one time and just sort of wish you the best, except they don't wish you the best because they're soulless machines. Instrumentation may be inaccurate. This is the Hubble Space Telescope being repaired. The lens was ground just a little bit wrong, so it was nearsighted. It couldn't see. So they're basically putting a contact lens in the Hubble Space Telescope. That added $10 million to the cost of that telescope. So when dealing with these complex real-time systems, right, an accident that takes just a few seconds to occur in real time makes man-months of effort to repair and diagnose. Repair if you can even diagnose it, right? So instruments can also be ignored. You know, you can work real hard to make dashboards and things for exploring, and the person whose job it is to watch these things and figure out what's going on gets bored. They play video games. They just stop watching. So accidents happen, and no one noticed. Instrumentation may also be used for undesirable purposes. So UPS is a great example of this. They increased the efficiency of their drivers by putting black boxes in the trucks. So UPS now knows all times where their drivers are and what they're doing. So between 1993, a good day was considered to be 75 packages delivered. Now it's 125. Unfortunately, they're watching their drivers all the time, and the drivers report feeling a sense of Big Brother watching them. So when you start building instrumentation like this, you have to recognize that complex organizations do evil things sometimes and don't do evil things as best you can. So what can we do to resolve these faults of instrumentation? You know, we've got our documentation, and we start adding instrumentation into them, and ideally we're getting better and better, but instrumentation has its own flaws. So what can we do? We write more documentation. In particular, you write documentation with the instrumentation in mind. So context reduces misinterpretations. You give people a better understanding of what that little dial means. Procedure manuals and visualizations reduce the need for a mathematics background. This is a navigational chart. I guarantee you most sea captains do not have a sophisticated understanding of trigonometry, and they do not need it. The more contextual layers you add, the more you reduce the big boards of blinky lights. So my boss, Valentino at Admiral, has a way with words. He's an Italian. His English is very good, and he has sort of a lyrical way of putting things. So instrumentation is like a suit, and it needs to fit your mind. So in the Admiral engineering team and in the operations, everyone has their own dashboard overview of the system. No one uses each other's instrumentation. We have documentation that refers to a common set, but we've all changed the instrumentation to fit our internal implicit models. So in the case of inaccuracy, cross-checks and documented error margins mitigate instrumentation inaccuracy. So if I happen to say in documentation that this meter only samples every 1/10,000th of events going through the system, because I'm doing billions of times, or billions of things a day, right? And I can't record them all. That needs to be known. You need to know that it's only a sampling, statistically significant sampling, but there is an error margin. My good friend Mike Sasek, who's at a company called Curbside, which you haven't heard of, but you will in about a year. If you don't trust a computer, because sometimes it doesn't tell you the truth, telling it to tell you to trust it is asking it to lie to you sometimes. The computer is in a divergent state. It does not have any understanding of the world, and you're now telling it to, okay, in your divergent state, report more stuff to me. It's broken. It can't do that reliably anymore. So once you recognize that you're in a divergent state, you have to recognize that your instrumentations might be false. So checklists with reference to instrumentation at decision points help solve the may be ignored. It can't solve the problem of an operator ignoring the checklist and then their oversight or manager ignoring that they're ignoring the checklist. So it ends up being a complex problem, a wicked problem. And for undesirable purposes, analysis of people's behaviors in kind of a creepy way. We have collaborative workplaces where that's just not acceptable culturally, cooperatives, unions, laws, et cetera. There are a lot of solutions to this, and we're just new at it, so we don't have a good understanding. UPS's union, for instance, does not allow hiring and firing decisions, raises, promotions, things like that, based on black box. That's really good. It helps get driver buy-in, so to increase the efficiency of the driver, get them promotions and things, but it doesn't enslave them to the sort of abstract system of UPS. Kurt Vonnegut thought a lot about this. Player Piano, if none of you have ever read it, is a techno-dystopian book, one of the first. And one of his characters who tries to smash the player piano but fails proposes this before he fails. Basically, when we build systems of control in terms of machines, we have to have humans in charge of them. Computers don't know about us, they don't care about us, and they can't be put in charge of us. So, instrumentation addresses the problems of documentation, and documentation addresses the problems of instrumentation. So, once you start adding this instrumentation in, you sort of realize that instrumentation becomes indistinct from your documentation culture. It is just something that you begin to do and must continue to do. Complex systems, especially, need them both. You must be able to have a shared understanding of the system, and you must be able to view the system. So for the engineers in the audience, or for the technical writers that have some sway with their engineers, how do you get started? If you use Erlang like I do, I highly recommend Exometer. It's a library from Foyer Labs. Ulf Vigger, are there any Erlang people in the house? Am I just, okay, a few, awesome. You probably all know Ulf. It's a great library, use it. If you use JVM languages, DropWizard's metrics is fantastic. It hooks into all the instrumentation that JVM has to offer and allows you to produce application-specific. Python scales. I am not myself a Python programmer, but Python programmers that I respect recommend scales. It looks really nice in practice. And if you need to catch these metrics, so if you're not a data company yourself, there are many services that allow you to view these metrics and build dashboards. AdRoll in particular uses Datadog. I love them. They catch 500,000 unique metrics from us at a gigabyte of traffic a second or something insane like that. I love them a lot. Questions? Oh, there's a microphone. I can't just point at you and hope you yell loud enough.
What advice would you give to the people who are writing the documentation for Google's self-driving cars?
Consider the case where a semi-truck slams into your car and drives it off a cliff. Every complex system will have some external event that drives it off into a failure state, no matter how hard you work. So I think a lot about self-driving semi-trucks, actually, because that makes a lot more sense, because you have drivers who, my grandparents are semi-truck drivers. Methamphetamine is a big thing among truck drivers, because if you can drive 16 hours, you can make a lot more money. So imagine a world in which we have a semi-truck and you have a technician sitting in it. They're able to sleep because the truck is driving itself. The technician has to have a glass display so they can figure out what the truck is doing. And the documentation needs to, at that point, be procedure manuals. So not unlike operating a power plant, because you can't service the vehicle as it's moving. And I rather imagine personal self-driving cars over long distances would be the same.
Anyone else? All right, thanks, Brian.
All right, thank you.